So the problem when we use some kind of problems when we use a linear regression model, that is we need to check some assumptions. That let's say if you want to draw a line between x and y, but the data of y variable is something like this. So if you draw a line, even if you draw a line, the residuals would be very high, and this line would be not much of a value. So even if you tell a computer to draw a line, it can draw a line, but between a perfect circle also, this will result in a low r square value. But before computing the low r square, we can check the assumptions before applying the linear model formula. So first assumption we need to check, there are some assumptions that we need to check. So first assumption is verify linearity. X and y should be linearly dependent on each other. That is, there must be a correlation between x and y which is some kind of linear. So this kind of structure where y equals to x square should not happen. So these are non-linear. Second is multi. So this happens only when all of the features are non-linear. Having a non-linear mapping with the target variable, the model is not effective, right? So we need some kind of linear feature, linear mapping of the independent feature versus the target variable, so that we can find the best fitting line between them, right? So even if one feature is present which has a linear relationship, it is good to go. Now second assumption is multi-collinearity. Features should not be dependent on each other linearly. For an example, we have these four features as total price equals to base price, discount price, and margin. So if you add, so total price is dependent upon base price, discount price, and margin. So if you include all these features into the model, so my final weight coefficient would be skewed up. So it gives the interpretation of the weight coefficient of the final model, right? So we cannot rely upon the final weight coefficients derived by the model, because my model has features which are linearly dependent on each other. So for that we need to check the VIF scores, whether my features are linearly dependent on each other or not. So if a VIF score lies between 0 to 15, which is a good range, generally should be less than 10, but if it's also less than 15, it's good to go for a feature that is an important predictor of the target variable. And so how do we compute the VIF score is also a very interesting thing to know. Let's say for features, let's say f1, f2, f3, f4, we have four features predicting the target variable y. So how much these three features can explain this feature can be determined by using a linear model or not. So let's say we train a linear model using these three features to predict this target. So if my r square is high for that value, so denominator would be low. So if the denominator would be low, minus, let's say 0.1, the r square is 0.9, 0.1 is 0.1, so VIF score is VIF score is 10. So we say that these three features can explain 90% of these three features combined can explain 90% variance of this the feature. So we say we have correlation, we have a VI score of 10. We suggest the multicollinearity exists. But what if it can explain the 100% variance of the hello hello हाँ हाँ here hello हाँ so it would be 1 by infinity. So 1 by infinity is not defined. 1 by infinity is 0. 1 by infinity 0, no, 1 by infinity is infinity. One by infinity is infinity. So we have a very strong correlationship and exact correlation existing between the features. Let's say this, right? Right. So to avoid this multicollinearity, we need to check this assumption. Now normality of residuals, normally distributed by, no, it's not a correct statement. Instead we should just check whether my distributions of the residuals are having a normal distribution or not using the QQ plot. If they are normal, according to some central theory, what you can say, central limit theory or central theories, and there is some central that says that if you combine multiple features of the variance to predict a value, the residuals should be in the normal range. Central limit theorem. The residuals formed should be in the normal distribution. If it's right skewed or left skewed, then the model is not able to find the best fit line. Model is not fit. Right? And we also have a homoscedasticity assumption which says that the variance of the error should be same across all values of y. So all values of y, not y prediction, all values of y. So for as my y increases, the error that my model is making should also stay the same. It should not, the variance should be same. But if there is some visible pattern like this, slope is increasing, that is called as heteroscedasticity, means as my y increases, my error increases. So for higher values of y, my model is making high errors. So which is, let's say house prices lying between 20 lakhs to 50 lakhs. My error is 50,000, but for 50 lakhs to 1 CR, my error is 5 lakhs. So as the value of y increases, my model predictions, my error is also increasing. Therefore, this is a case of heteroscedasticity. So this should not happen. Even this suggests the model is not a good fit. Yeah. Thank you. So these were the assumptions of the linear regression model.